Hi everyone, in today's video we are going to start talking about normal distributions, and that is going to start with a conversation about the empirical rule. So in this video we are going to learn how to label a normally distributed curve using the mean and standard deviation, and then we're going to apply knowledge of the empirical rule to find percentages, probabilities, and other likelihoods. So we need to do some vocabulary first. We are going to use some Greek letters continuing with our stats unit. So we first need to talk about what an average is. When we have an average, you've likely calculated these before in other classes. If you have, say, a bunch of grades in the grade book, to find the average of those grades, you add them all up and then you divide by the total number of grades. And that finds our number that represents the middle or the center of the data values. So we are going to use this Greek symbol mu. It looks kind of like a fancy M or U, if you will. I like to think about it as an M for mean, to stand for mean. So let's look at a quick averaging or mean example. So if you have the data set 0, 2, 3, 7, and 8, to find the mean, we add up all of those numbers, and then we divide that sum by the total number of data points there are. So in this one, there's 1, 2, 3, 4, 5 numbers in our set, so we're going to divide by 5. When we add all of that numerator up, that gives us 20, and 20 divided by 5 is 4. So that means the average number in our data set is 4. Now, the other vocabulary that we need to talk a little bit about is called standard deviation, and we're going to use this Greek symbol that kind of looks like an O, a cursive O, to represent that. So what the standard deviation does is, once we know what the middle is, the mean, the standard deviation tells us how far away from the mean all of the other numbers in the data set are. So it tells us how distant we are, or how deviated we are from the average in the middle. Now, there is a formula for each of these. For means, you do not need to memorize this formula. It's just adding together everything in the set and then dividing by the total number. If you understand that concept, there's no reason to have that memorized. Standard deviation, we are not this year going to calculate by hand. We're going to be given the standard deviation and we're going to use it. So you don't need this formula, but I do want to point out that the formula has a summation in it where you're summing things together. So I just want to point out that there is a connection between what we're doing with normal distributions to what we were doing with series in previous lessons. We're just not going to have to do all of that legwork. That legwork is going to be done for us already. Okay, so let's get into what a normal distribution is. If you have a data set, so a set of numbers, and it's modeled by this bell-shaped curve, meaning that you put all of the data on a graph, and it makes this really nice symmetric curve shape where the average is in the middle. So this is our mean. That's called a normal curve or a normal distribution. So when we're looking at these normal curves, we're looking at our x-axis. So these are going to be values where, like the 4 from the previous example that we did, would be in the center. That's our average. And then we would count numbers to the left and right. So if we wanted to find, for example, how many numbers, or what number was the lowest, like 25%, like where's the 25% mark, we would shade up to wherever that 25% mark is, and then that number would be the number on the line there. So we could read this as the area under the normal curve. That's the thing that I shaded. The area can be interpreted as a percentage or a probability. So if we're looking for the x that covers this 25%, or say we're told that we're looking at, say, 6 as a number, and what percentage of the data is it bigger than, those sorts of things. So we'll get into some questions like that in a moment. But to help us with that, there is this really great rule called the empirical rule. Sometimes it's also known as the 68, 95, 99.7 rule. And this is something that you're going to have to memorize because it's going to make everything super easy if you have these numbers in your head. It is non-negotiable today. So the rule says that if we start with the mean at 0, in this example, or in this formula, if we go one standard deviation above the mean and one standard deviation below the mean, and we're looking in this set here, the purple section of the graph, then 68% of the data, or 68% of the data set, is going to be in that area. If we go 2 standard deviations out, so now we're looking at the pink and the purple section here, that's going to be 95% of our data, so almost all of our data. And if we go 3 standard deviations out, that means we're looking at the red shaded area, the pink shaded area, and the purple shaded area, so all of this, then we're looking at 99.7% of the data. So almost absolutely everything. Only 0.3%, which is a tiny little bit, is missing. So let's look at how that's going to help us by doing some labeling here before we get into an actual problem. So we know that we can always label the mean immediately with whatever the average is. And then if we are going to one standard deviation to the left and one standard deviation to the right, that means the area of this section of the graph is that 68%. Now 68%, if I divide it in two, if I divide it into the left side and the right side, 68 divided by 2 is 34. So that means this section is 34% of the graph and this section is 34% of the graph. Those numbers are going to help us calculate when we get into some problems in a moment. If we're looking from the middle, which is our mean, 2 standard deviations, 2 to the left and 2 to the right, we have this middle section that's 34% and 34% to make our 68% total. And if we know that these 2 standard deviations here, if we shade all of that middle area, that's going to be our 95%. If we take our 95% and we subtract our 68%, that means we're looking just at these outer wings here. And if we take that, difference and divide it by 2, that's going to tell us that this and this, and that's going to be 13.5%. So that means this left area is 13.5%, and this right area is 13.5%. Again, these little numbers are not numbers that you have to memorize. You need to memorize the big ones, 68, 95, and 99.7. But these little numbers are going to make it easier for us to answer problems in a moment. So I'm going to highlight these little numbers for us because they're not required to memorize, but they're certainly going to make our lives easier and we're going to have less work to do if we do have them memorized. The last one that we need some extra numbers are 3 standard deviations away. So if I go from my mean, 1, 2, 3, so we're looking at almost the entire graph here. We are not looking at this little outer bit out here yet. So we're going from 3 standard deviations away from the middle on each side. We're looking at all of that. We know that these are each 34%. We know that these are each 13.5%. And if we're trying to find this area here and this area here, we can do what we had before. So we can take our 99.7, subtract our 95%, that's the stuff I haven't shaded, and divide it by 2 to get these 2 bits. And when we do that, we get 2.35%. Okay, so the last part that we need is when we go out beyond that piece. So we're talking about this section over here now. We're looking at this little bit out here where almost nothing is. It's the last bit of the 100%. So 100% minus 99.7 is 0.3%. If I divide that 0.3% in half, that gives me 0.15%. So I've got this tiny little percent over here describing this last bit and a tiny little bit over here. Okay, so I know that was a whole bunch of calculation. The numbers that I have in clouds here are the most important to remember. The highlighted numbers are going to be very helpful to you to remember, and we'll see why in this next problem. So let's go ahead now that we have these numbers written down so that we can refer back to them often. Okay, so let's read this example together. A machine fills 12-ounce potato chip bags. It places the chips in bags. Not all bags weigh exactly 12 ounces. The weight of the chips placed is normally distributed with a mean of 12.4 ounces with a standard deviation of 0.2 ounces. The company has asked you to determine the following probabilities to aid in consumer relations concerning the weight of the bags purchased. Okay, so think about being in the grocery store for a minute. You are on the potato chip aisle. You are about to grab a bag of potato chips. On the package, that potato chip bag is going to say 12-ounce bag. Now, machines are pretty accurate, but they're not perfect. Potato chips are also different sizes, and stuff gets complicated in the factory where they're packaged, right? So the company has decided and got the machines to put an average or a mean of 12.4 ounces, that's our mean, that's our middle, in each bag, which means technically you're getting 0.4 more ounces of potato chips than the bag says. That's good news, right? But there's also a standard deviation of 0.2 ounces, which means that there's some variability. Not all bags have 12.4 ounces, it's just the average. So what we're going to do to get these other marks on our x-axis at each of the standard deviation marks is we're going to take that 12.4, and to do the right side, we're going to add 0.2 and get 12.6. That's one standard deviation. Then we're going to add 0.2 again. That's going to give us two standard deviations, and we're going to add 0.2 one more time to get the third standard deviation. We're going to do the same thing on the other side, but this time subtracting. So 12.4 minus 0.2 gives me that tick mark. When I subtract 0.2 again, it gives me the next. And the third tick mark when I subtract 0.2 one more time. So now I have an x-axis on my normal distribution. So we're going to look at some probabilities that the potato chips in the bag are more or less than 12.4, the average. Okay, so if we purchase a bag filled by the dispenser, what is the likelihood it has less than 12 ounces? So on our normal distribution, we know that our average, or our mean, is 12.4. We also know by the labeling I just did that two standard deviations to the left, that's where 12 is. So if we want the likelihood it has less than 12 ounces, that means we're going to draw the line at 12, and less than, we're going to shade the smaller side of the x-axis. So we're looking at this far side to the left here, up to the 12. So there was that third standard deviation mark at 11.8, and then there's this second one. All right, so now is where those rules from a moment ago are going to come in handy. Specifically, I'm going to use these numbers here because look at that shading there. I shaded from the end of the graph up to that second on the left standard deviation mark. That means then that I can do that same labeling on this one. I know this section is 0.15% of the graph, and I know this section is 2.35% of the graph. So I can do 0.15 plus 2.35, and that gives me 2.5%, and that is the likelihood that our bag is going to be less than 12 ounces. So it's a pretty small likelihood that I'm going to get a underfilled bag, 12 ounces or less than 12 ounces, only 2.5%. So it's working in my favor that I'm not going to have to call customer service and complain about my empty potato chip bag. Let's look at another one. If you purchase a bag filled by this dispenser, what is the likelihood that it has more than 12 ounces? So we're still working at that 12 ounces mark. Our middle is still 12.4. Still 2 standard deviations to the left at 12, but this time we want to know what's the likelihood or the percentage of chance that we're going to get a fuller bag than what the bag says, 12 ounces. So on this one, I'm going to shade this section all the way to the right because I want to know the likelihood that it's any of these X values bigger than 12, because this is going to make me happy, right? If I get a potato chip bag that has more potato chips in it than the package says. Now, I could add up all of these little percentages. I could do 13.5, 34, 34, and so on. That's one way to work through this, but that's a lot of little percentages to add together. Let's be a little bit more strategic about this. I'm going to change my color. Another way that you might choose to do it is knowing that this is the halfway mark, which means that this section of the graph is 50% because it's half. Then we could do that 50% plus these other two percentages that we know that we needed to get our percentage for the whole red shaded region. Another way that we might think about this is because we just did the last problem and found the other part, right? We know this section over here is 2.5. That means the whole thing is 100%. We can also subtract the 2.5% and get our answer. These two ways will get us the same answer no matter what we do. We could also add up all of these little numbers and get the same answer. It's really up to you how you choose to approach it once you have the graph shaded correctly. Whichever way you do it, you're going to get 97.5%. which means there's a 97.5% likelihood that we are going to get more potato chips in our bag than the bag says it's going to have in it. Let's look at some more examples because the shading's going to get a little tricky on some of these. If you purchase a bag filled by this dispenser, what is the likelihood that it has less than 12.6 ounces? So in this one, we are going to be shading a little differently. We're going to label our mean of 12.4. And we're going to label the 12.6 that the question's asking about using our standard deviations from when we did that first labeling. That's up here. So then if we are doing less than 12.6 ounces, that means we're shading on the side where the numbers are smaller and trying to find that shaded region. So for this one, I think I'm going to use what I was doing in blue just a moment ago because I've got half of the graph shaded and then a little bit more, right? So I have 50% of the graph right here. So that's 50%. And then this section is one standard deviation away. So that's 34%. So I'm going to add the 50 plus the 34. That gets me the whole red shaded region, which is 84%. So I know that there's an 84% likelihood that I'm going to have less than 12.6 ounces. The next one says if you purchase a bag, what's the likelihood that it will be, this time between 12 and 12.6 ounces. So I'm going to label my middle at 12.4. I'm going to label my lower bound or my minimum, and I'm going to label my upper bound or my maximum. Those again came from that grid or that normal curve that we labeled up at the top. Between means we're looking in between these two numbers. So we're looking at all of this region. So I think for this one I'm going to use that 68% that I had a moment ago from my rule. So I know that one standard deviation to the left and one standard deviation to the right. So this section here is 68%. And then this little section we calculated was 13.5. So that means that 68 plus 13.5 will give us the total blue shaded region, and that's 81.5%. All right, the next one, the question's a little different. What weight of a bag? So this is the x-axis. The weight is what x is equal to. So I'm being asked a different question here. What weight of the bag is represented by the 84th percentile? So that means I need to shade. Percentile means up to that percentage. So I'm going to start on my left and shade up to wherever I get to 84. Now I could start with these tiny little numbers down here, but again, I know half of the graph is 50%. So I've got that 50%. I'm not going to add up all of those little pieces. I'm going to add up the 50, and then I'm going to add on just one standard deviation more. So let's add on this section here and see how close that gets us. That's 13.5. And 50 plus, no, not 13.5, goodness, 34%. 50 plus 34, oh my goodness, look, that is 84%. So that means that to get up to 84%, or the 84th percentile, all of this, the x value, that's what number is down here, that x value was 12.6. So when the weight of the bag is 12.6, that's when I'm in the 84th percentile. All right, let's do another one of those. A weight in what range would represent the bottom 16% of the weights? So I'm starting at the bottom and I'm going to shade to the right until I get 16%. So for this one, I am going to start with the little numbers. So this tiny little section over here, that's 0.15. I'm going to add in this next section here, which is 2.35. That gives me 2.5%. So I've got a ways to go to get to 16 still. So I'm going to add in another standard deviation. That's the section here. That is 13.5%. So let's add in that. When I add those together, that does get me to 16%. So that means then that I'm looking for the weight, that means that x value of that standard deviation. So compared to the mean, that was one standard deviation to the left, which means that that x value is going to be 12.2 based on the labeling that I did earlier. So the bottom 16% are going to weigh less than 12.2 ounces. Okay, let's look at a couple more examples before I send you on your way. The blood cholesterol readings for a group of women are normally distributed. That means I can draw a curve with a mean of 172. So I'm going to label my 172 in the mean, and a standard deviation of 14. So that means I'm going to label my curve by adding 14 to each number to get the right side and subtracting on the left side. So 172 plus 14 is 186, and then 200, and then 214. So again, I was taking my mean and I was adding the standard deviation of 14 each time I went out another deviation. Now to go to the left and get that part of the x-axis, I'm going to subtract 14 each time. So 172 minus 14 is 158. 158 minus 14 is 144. Minus 14 again is 130. So I've got my x-axis now. Let's get into some of the problems. About what percent of the women have readings between 158 and 186? So I've got my mean of 172. I'm going to label, see, the 158 was one standard deviation to the left, and the 186 was one standard deviation to the right. So that means I'm looking at the area shaded between those two values. This shaded region, remember, was the middle section of the graph. That's 68% according to the empirical rule. Let's look at one last one. Readings higher than 200 are considered undesirable. About what percent of readings are undesirable? So from my mean of 172, I'm going to draw a line at 200. And we're looking at the readings that are higher than 200 if we want the undesirable ones. So that means we're going to shade the section higher than, or that's our undesirable region. So let's see, we went out 2 standard deviations to start, and then we shaded the last one out here and also the second to last one. So the last one is 0.15. The second to last one, is 2.35. We're going to add those two together, and that gives us 2.5%. So 2.5% of the readings are going to be undesirable, meaning that they're more than 200. Okay, so in this video, we learned how to label the normal distribution curves using the mean and standard deviation, and then we used the empirical rule, which you absolutely need to memorize, to find percentages, probabilities, and other likelihoods. Go ahead and try the Now You Try problems.